So my name is Klaus Mühlhans. I will guide you through that session. And we start with Michael Elstner. He's from AGC Europe. And he's the manager of technical advisory service at AGC Glass Europe. And he will give us a presentation about optical distortion in tempered glass, a claim or a feature, and how to visualize it. Now let's see, is it a claim or a feature? He will give you the answer. The stage is yours.
I hope you're fresh and awake after the evening yesterday with the dinner. So some words about this topic. I hope they can switch to the screen, to the large one, not just from my screen. Now it's there. So, all right. Yeah, what do I want to show you this morning? A short introduction to the topic. To go back first, so it's on behalf of Louis Deleu and Chloé Théroux, my colleagues from Optical Digital. So I'm working for AGC Glass Europe as introduced before, and they are working for Optical Digital, and I do this presentation on behalf of them. My focus is more on the application of this virtual prototyping tools, and not so much on the simulation side. Yeah, just a short introduction. I show you the 3D model which we have considered, and the environment we have considered, the glass configuration, and which optical distortions we have simulated. And I show you some results afterwards, some nice pictures, so not so heavy stuff, and a little bit different to the talk before. Yeah, is this flat glass? So if you look to old windows, you saw this drawn sheet glass types from the past, from the last centuries, and yeah, some 100 years ago. This is not really flat glass. So if you look to the standard for soda lime silicate glass, you see that a float glass is a flat, transparent glass with parallel and polished faces, and it has a very good optical quality. And this is a typical annealed glass which we are using in architectural practices, and you can further process these products to other glass applications like insulating glass units, thermally toughened glass, where we focus on now in this presentation, and laminated safety glass. Yeah, if you remember back to the toughening process, so I assume many of you know how glass is tempered. So it's first of all it's heated up to around about 650 degrees. And it is reaching its viscoelastic state, and it's oscillating on the rollers, which have different diameters and distances as well in the tempering furnace, especially in the heating chamber. Glass is oscillating over these rollers. It's getting soft, I would say, and it's lying a little bit over these rollers. And this means, when you look to the standard as well, you can't get, which is inherent to the tempered glass, a flat glass as annealed glass as described before. So this means it's typical that tempered glass has another type of flatness, as it is distorted, distortions and different kinds of distortions, which are also described. You see here the overall bow, you see the roller waves, which are the most prominent ones, the edge lift or edge dip it's also called, and for another type of tempering furnace on air cushion processes, it's the perimeter deformation. So this is something what we don't want. So this is the short waveness, I would say, of glass, and you see roller wave distortions in different extensions. So we don't want to get that, but we can't avoid it. And what is the extent of these flatness tolerances? We must make samples normally. So you must make physical samples to show it to customers, and how to visualize this in real life. What does it mean to have a certain distortion value? But we have also other types of distortions, like the climatic effect of insulating glass units, which we didn't address here in this study. So it means if you sum up the type of distortions, we have the roller wave and edge dip, edge lift distortion components, I would say, of heat-treated glass. It does not matter if it is a really fully tempered glass or if it is a heat-strengthened glass. But we have also others. So you have the overall bow, we have the climatic loads, and we have additional external loads like wind loads. And all this comes together in an overall deformation. And the question we had is, do we always need a physical sample to highlight and to address these distortions? And with the help of the current computer simulation tools and the computer power we have now, we can also visualize a certain extent of these distortions. So we can limit but not avoid mockups. So this is time consuming, expensive, taking a lot of resources to do all these mockups. We can't avoid that, but perhaps you can limit the number of physical mockups. So we all talk about sustainability and all these things. And is it really necessary always to use physical mockups in a huge number, or can we have alternatives? And again, with the help of computer simulations, what we did in this study for us, first internally, we wanted to highlight the different extensions of the distortion values as highlighted from the standard. So for this study, we simply considered a pane size of 1.6 by 3.6 meters in a double glaze unit. We have aluminum spandrel, not a glass spandrel. We have a 50-story tower located in a city with the surroundings, other buildings around, and this was the simulation. So these buildings are simulated; they are not real. And we have also considered two different environments, because you will see later in the results that the environment plays a dominant role in the visibility of the distortion. So if it is a sunny day on the left-hand side or it's a cloudy day, it makes a huge difference in the visibility of the distortions. So this means we have simulated based on real location pictures, transferred in an HDRI map, a sunny day and a cloudy day. Yeah, what IGU properties did we have? As I said before, we have a double glaze unit. Outside glass is a tempered glass, 8 mm, stop revision, 50 coating, low iron glass, and the inner light is a laminated safety glass with a PVB interlayer. So we need the spectral data, because this kind of simulation is a virtual prototyping, virtual rendering, which is based on real spectral data, which means data per wavelength. It's not integrating it. It's using really spectral data and then integrating the data, not to use integral data from the beginning. And the overall data are displayed here. So we have a light transmission of 50. Important is the light reflection. On the left side, you see the external light reflection of 90%. And this is just the basic figures which are important to visualize finally then the image and the distortions. Yeah, what did we consider? We have case 1, 2, and 3. We have considered 3 cases for this double glazing unit. We have, as you can perhaps remember back to the product standard of tempered glass, the overall bow 3 mm per meter, and roller wave distortion of 0.3 mm per 300 mm. This is a standard tolerance. So with that, you get a really high distorted pane. You will see later. Then we have case 2. Which is an optimized one, and a really good one is case 3 with 0.15 millimeters, focusing on the roller wave distortion over 300 millimeters. Then we have combined all these tolerances, as you can see on the left image here below. The overall bow is over the height, because it's we assumed that the tempering was taking place with the short edge first, and then the long edge was coming, so the trailing and the leading edge, and which means we go over the 3.6 meters, and the roller waves are parallel to the width, which means parallel to the 1.6 meter edge. This we have then combined in a distortion image, let's say. You see here the extent on the top for each case, and on the bottom you see already the pane, 1.6 by 3.6 meters, and how the extension is of the overall bow together with the roller waves and the edge dip. The edge dip and edge lift is mainly on the leading and trailing edge, and the roller waves are all over the height, and the overall bow, it's clear, as a matter of fact, it's like a bowl. It's the highest deflection you get in the center of the glass. Knowing that it's a little bit coming up on the edges, but for the simulation it does not really matter. So we have combined all these values, and you see here the overall distortion is reduced. The overall bow is much clearer and lower, as highlighted in the values. Yeah, what does virtual prototyping mean? So it's a physical, realistic ray tracing simulation or calculation. So it's really following up the reflected arrays which are sent from an illumination, so from the environment. It's reflected from these 3D boundaries or models, and really calculated wavelengths by wavelengths. This gives a very exact a model and a very exact image afterwards. As already mentioned, we have real spectral data of each material, so we have not integrated the values before. We use really the measured data for each material, and we have now after processing, post-processing with a computer, so it's not a post-processing system or calculation. Yeah, each of the renderings or techniques has its use or it's necessary. But the computer-generated image is like that. Just to give you an idea, it looks like that. The virtual prototyping looks like that. So you see also already a slight difference. You see a little bit more the reflections and difference in color, a little bit more concrete. And if you compare it with the final picture of a building, you can assess for your own what is more close to the reality. Is it the CGI rendering or is it the virtual prototyping? So the virtual prototyping gives you a lot of possibilities, not only in architectural markets. You can use it for every application, for every product, to visualize it finally. Now we come to the results. We considered in the study two different, let's say 3 different viewing points. As I said, we have an urban environment. We have high-rise buildings all around. The building we have considered is 50 stories high. We have 40 meters distance and 50 meters distance. We have a viewing angle of 45 degrees. And we have a more acute angle. You will see we have a more shorter distance with a more acute angle in one other position, which is not shown here. But if you stand on the opposite side of the considered building, you have sometimes also a special view to it. So all of you have ever visited urban cities and looking at glass differently, not through the glass, which is typically for glass, but if you look at glass, as we have to do it in our job, then you see at different positions, different kinds of distortions, and it's really variating. So in this talk in the morning, I have the pictures for you for a 40 meters distance and a 5 meters distance, a cloudy day and a sunny day, not the 50 meters. So if you're interested on that, we can have a talk later or anyway, but I just show you to highlight that. So if you consider no deformation, which means we have no tempered glass, let's say we have annealed glass, it looks like nice, smooth, and like that. I will not speak too much when you see the results, but you can see yourself. I have mentioned again the tolerances for each case. We have now here case 1, 40 meters, cloudy day. It's already distorted. No surprise on that, because we have a very high tolerance for the roller wave distortion and also for the roller waves. But no, it's getting better, as you see here. So I go back here to this slide. It's getting better. And the improved version with 0.15 millimeters, it's getting much better. So this is the cloudy day. It's hard to record that in the mind, so I can go back afterwards again. And now we have randomly collected all the distortions, how it can come. Not in a sequence as I have explained before. It's randomly applied, and you can see as it is sometimes in reality, because tempering and processing glass is not always straightforward. So it could be also randomly applied to each pane. So a building could look like that as well. But again, back the optimized version and the high distorted one. If it is cloudy, sunny, the flat pane again. So very nice sunny day as we have it this week in Finland. And then we have again the tolerances. You see here, case 1, case 2, case 3 optimized. But as you can see, on a cloudy day, it's more prominent, more visible, the distortion. So it's really dependent where you stand and in which weather conditions you observe the glass. And again, randomly applied. Now we stay close to the building, let's say. We have a very nice flat surface again. The color is shown from the coating very nicely, and you see the distortion here. So we have now a very acute angle, a very short distance. So no one wants to have that, so we have to improve it. You see it here, still wavy, and the improved version. So it's getting better if you improve your process, the tempering process, and you can also still highlight some small deviations. So we can also go down to 0.10, 0.008 as it's sometimes specified to discuss these small deviations into tolerance values if it does really matter finally. And then you can further discuss this matter. And the sunny day, it's less prominent. You still see the distortions, yes, it's a matter of fact, but less prominent. So you see here, again, the pictures and randomly applied. So to conclude, with the help of the virtual prototyping simulations, we are able to simulate different types of properties of glass, not just colors, to compare different products to each other, but also processing tolerances. And you can apply this technique also to other things in the architectural business or other businesses. So we wanted to highlight that, to open the discussion and to use these possibilities to discuss about the tolerances without physical samples. So that's it from my side. So I promised you to have pictures and not so much technical details. So yeah, I'm open for any questions. Thank you for listening.